it's already evening in India, afternoon in Poland. So it's great pleasure to welcome our guests from Madras, from Chennai. You see the presentation of Arul Lakshminarayan, who visited us a few times in Krakow personally. Now he only uses possibility to for a virtual visit in Krakow. We just had some snow in Krakow. Now it melts down, but new is coming. So you are not going to witness winter in Krakow, and you are going to talk today about new results concerning quantum chaos and quantum information. And you will tell us, I hope, what are the Bernoulli circuits and their quantum version. Yes? So, Arul,
Yep.
thanks again, and the screen is yours.
Thank you, Carol. Thank you, everyone, and thank you for the invitation to present our work. It's posted, I think, barely 10 days before in the archive, and so I'm happy to talk to you about this and get your valuable inputs. Already, Carol has given a very interesting feedback, so I hope that this talk will also be of interest to you, and we will get some interesting feedback. So what I'm going to talk about is, well, I changed the title a little bit. I put an A before the road because I guess there could be many roads, and as I will indicate at the end. And so there is a road to quantum Bernoulli circuits, and I hope it's not. I'll actually introduce what I mean by this, but my starting point is really classical. And there is in classical dynamical systems which are ergodic. There is an hierarchy which is often called the ergodic hierarchy, which at the bottom of the hierarchy are ergodic systems. Ergodic systems are typically characterized by the statement that some phase space average is equal to a time average. And that's at the base of the ergodic hierarchy. Climbing up this ergodic hierarchy, we go to mixing systems, which are exactly what we think about as mixing, that putting ink and water and mixing it up and so on. So what happens here is still a measure preserving transformation. So it's still Hamiltonian in a sense, but any initial density tends to get mixed over all phase space eventually. And these two are kind of assumptions in all statistical mechanical systems, but even very simple dynamical systems display these things. And typically, actually, mixing systems are more or less what we would call chaotic systems. But to be more specific, there is an in-between point which is often called Kolmogorov systems, K systems, which are characterized by some positive entropy production, as well as by a positive Lyapunov exponent. So typically a chaotic system is Kolmogorov. We'll come back to this. And what we call chaotic systems in classical mechanics are typically, or classical systems are typically Kolmogorov. And at the sort of the apex of this hierarchy are Bernoulli systems, which are although completely deterministic, and that's what we're talking about, no source of external randomness, they are, in a sense, very chaotic in a way which I will indicate shortly. So,
Arul, a silly question. What kind of mountain you show here? It's not K2, neither it's not
no, it is, well, it's Kanchenjunga.
Kanchenjunga. Ah, Kanchenjunga. Okay, now I see. Okay. Thanks for this explanation.
Yeah, I, of course, vandalized the Kanchenjunga thing. Well, I know that you're a mountaineer, yes. But I would badly go to the base camp. That's 5,500 meters.
Okay, thank you for this explanation. Yes.
And so, just to give you a visual idea of what an ergodic system, but not a mixing system is. So I should mention what is the meaning of this is that ergodic systems I mean, in this hierarchy, a Bernoulli system will be Kolmogorov, a Kolmogorov system will be mixing, but not the other way around necessarily, and a mixing system will be ergodic. So all of these are ergodic systems, but Kolmogorov and Bernoulli are mixing, etc. So an ergodic system, but not a mixing one, is something which is going all around the phase space, but phase space densities are not getting mixed. So here is a simple example of that. It's just a area preserving map on the plane, in fact on the torus, which is just doing this. On the other hand, if we modify this transformation, still it's area preserving. Here is the famous Kant map. You can see that just in a few iterations, it has mixed that same initial density which was there, and now it's just more or less, it's in an equilibrium kind of situation. So this is ergodic and mixing. We can barely see any differences with a Bernoulli system from this point of view. So what characterizes the differences are correlations. Correlations is one good way of differentiating between these different types of ergodic systems. So let's take the simplest correlations of just two functions. So f and g. So g, x here is a generic phase space variable. And take two functions on the phase space, keep one unevolving, that is g, and evolve the other function along with the flow. So the flow is given by this phi t, and t is the time. Okay, so we are evaluating the function at phi t, and then we are finding the correlation with this function g of x. And so this is the correlation function after a time t. The various different classes have the following properties. If it is ergodic, then the infinite time average of the correlation vanishes. Okay, so the correlation for any functions f and g, reasonable functions f and g, the average correlation vanishes. If it is mixing, then you don't have to take an average. With infinite time, as time goes by, it strictly goes to zero. So this correlation itself tends to zero. By the way, the brackets here indicate a phase space average. So it could be with respect to an invariant measure. Like if you are talking about Hamiltonian systems, this is just the usual Lebesgue measure, or just the volume in phase space, which is what we will have in mind. So the mixing systems are characterized by the vanishing of these correlations at infinite time. A Kolmogorov system, unfortunately, doesn't have a very simple or straightforward characterization in terms of these correlation functions. But we would, as I said earlier, characterize it in terms of positive entropy production, positive Lyapunov exponent. In terms of these correlations, I would say that as long as this mixing is happening exponentially fast in time, the system is Kolmogorov. And then these exponential rates are associated with some resonances, the Poincaré resonances. A Bernoulli system, on the other hand, is specialized, is even more special. It doesn't just exponentially decay with time. There are special correlation, there are special functions f and g such that it instantaneously decorrelates, is equal to zero as long as time is greater than zero. So there is the past has no role to play in a Bernoulli system as long as these observables are what are called Bernoulli partitions. So Bernoulli, this partition is a partition of the phase space. It's a complete partition of the phase space. And this particular partition of phase space then leads to symbolic dynamics. And if you look at the symbols in that dynamics, it's isomorphic or equivalent to something like a coin toss. So the usual slogan is that Bernoulli systems are as random as a coin toss, although it's a completely deterministic system. And a classic example, which goes back to, I think, Hopf in 1930s, is the Baker's map. So it's an area preserving map. So here you have Q and P going to Q prime and P prime. The Q prime is just a doubling map, so it just gets stretched by a factor of 2 and compressed by a factor of half in the momentum direction, which is the vertical direction. So here is the baker kneading the dough. So that's the scenario. And this is a Bernoulli system. And the dynamics is just a left shift on binary symbols. So the Bernoulli partition here is again very simple. It's just partitioning the phase space square into a left and a right vertical halves. So these are actually Bernoulli partitions. So that's the hierarchy. And what we will be doing is constructing or looking at quantum systems which also have a very similar phenomenology.
It's interesting.
So there has been, of course, many studies of quantum chaos. It's a very old subject from at least 40 years now. But I'm going to talk about some particular kind of models which are space-time models. So it's not just a one-dimensional system. So it's on 1 + 1 dimension, there's space and time. And they are characterized as these kind of circuits. And there are interesting things which can be done analytically as far as these correlation functions, especially these correlation functions are concerned. And therefore, they already construct some kind of an ergodic hierarchy in quantum mechanics, although there's no phase space and so on, which is the setting of classical dynamics. So there is a prehistory to this, but I'm going to follow closely initially this particular paper from which of Bertini, Koch, and Prozin about exact correlation functions of dual unitary lattice models in 1 + 1 dimension. But there's a prehistory which goes back to at least 2016, 4 years back. There's classical foundations of many particle quantum chaos and a kind of duality which was found in Ising spin chains. And then there has been several recent works by the same groups and by others also. There's a very nice paper by Claes and Lamacraft, who in this paper you can they give a different, slightly different view of this, and also I think calculations of out of time order correlators and so forth. Okay, so what I'm just going to give a brief introduction to a kind of a tutorial, if you wish, of these circuits. So it's best done visually rather than calculation. Therefore, we can draw, motivated by things like tensor networks and these such like pictures. So here we represent a unitary operator U, and we are going to consider at this point the unitary operators are going to be constructed by two particle unitary operators. So consider just a bipartite unitary operator for the moment. So it's, let's say, acting on a Q into Q system. So Q is the dimensionality of each of the subspaces, and represent the unitary operator like this. So here is J beta. This is the input, if you wish, and the unitary operator itself is the square, and that's the output legs. Okay, the adjoint is represented by another color, but otherwise it's the same. So here is the UU adjoint because it's identity. This multiplication is just contraction of these legs, and this is the identity that UU adjoint is identity, or is equal to, is identity. So this is just contraction of I with J and alpha with beta. And similarly, U adjoint U. So you read from down up. So first U adjoint and then U. And here U and then U adjoint is identity. So a tensor product of several such operators is simply given by this. So here is 4 of these bipartite unitaries, tensor product of them with 8 particles. So do we construct the Floquet operator, which is our central object, in a 2-step process? So first we have first of all, let's have an even number of particles. And we have nearest neighbor interactions, which are given by these unitaries. So U1, 2 is this, U3, 4 is this, etc. So that's this tensor product here. And then in the next layer, you have the interactions between 2, 3, the other neighboring pairs, which are got by a translation of this. We assume periodic boundary conditions in position. So, so this together forms one Floquet step. So this is our dynamics. So the dynamics is a Floquet operator, an unitary operator on q to the power of 2l. There are 2l particles in this system. So here is the full unitary operator. So this is the two-particle unitary U, which will play an important role, which is tensor product L of them. And then there's a shift here. So you're just multiplying the whole thing there. This takes care of this shift here. So T is just shift by one lattice spacing. And the dynamics on these 2L particles is just the power of this grand unitary operator. So there is a certain interesting space-time duality, which is from a statistical mechanics point of view, sort of when you're calculating the partition function, you're doing a transfer operator method. So that's essentially the same kind of a thing. But let us say that we want to calculate this object, which is the trace of the propagator raised to the power of time. As you know, that's an important quantity from which a fair amount of information can be gleaned. So how does one do this? So we just put up layers of this circuit. So this would be 10 particles, because you have 5 of these out there, and 2 of these layers constitutes one time step. So this is 3 time steps. So this would be u to the power of 3, and a trace operation would just so this would in time there is this. I mean this trace here would simply contract all of these all of these legs, and the periodic boundary conditions would contract these legs on the vertical. Sorry. So this whole thing is on a torus, if you wish, and that is what this trace u to the power of t is simply this diagram. Now, what one notices is that we can view this slightly differently. Instead of viewing this as something which is going from vertically from bottom to top, we can view it as something going from left to right. It looks the same. It looks the same, except that now our contractions are happening in different direction. And therefore, we can actually view this as something which is now trace of u tilde to the power of L, where now this L is the number of blocks here. So that would be here 5. And this u tilde is looking at the same unitary operator, but now looking at it from a spatial direction. Okay, so this is the change of viewpoint, but there is the space-time duality that this trace of u power t is also a trace of u tilde to the power of L. So you can trade time for space when you're trading this unitary u for an u tilde, where this u tilde need not be in general a unitary operator. And in general, it's not a unitary operator. So 2L particles, propagator u over a time t, can be considered equivalently as 2t particles. Propagator is u tilde and a time of L. Please do stop me for any clarifications.
Well, now it looks perfect for me, but are there any questions from the audience? Not yet. So Thanks. Please continue.
So, now we will define the case when this u tilde is also unitary. So in that case, we would call this, so that follows from some particular property of this two-particle unitary u itself. And that property is what what was called dual unitary in this paper, because it leads to this duality, the dual circuit also being unitary. So U is dual unitary if the contraction along the spatial direction, so the horizontal directions, is also unitary. You see, the usual contraction was along the vertical direction here, and that was identity. So now you require that also now you require that the contractions along the spatial direction, and by spatial direction now I mean the ones which are here on this, that also is identity. So when you're contracting this, so that leads to identity. So basically this goes away. And similarly, this one out here. Now, if we follow this through with indices, let us just follow this through the indices. The green one here is this sort of green operator here. So there'll be I1, alpha 1 as inputs. I should read this as I2 alpha 2, I guess. I2 alpha 2, and then there is U, and then I1 alpha 1. And then there is U adjoint, I1 alpha 4, and I2 alpha 3. So what is contracted is this I1 and I2. So those are these two.
Indices which are repeated are contracted, yes? With some of the repeated indices.
Yeah, that's correct. Sorry, I didn't write the summation. So the repeated sum indices are being summed up over. And so that's equal to this. But we recognize this as nothing but a rearrangement of this unitary operator. And therefore, we can write this equation as precisely this, where this rearrangement of this operator UR2 is by definition this. So, so this is actually the way in which I think Carroll especially studied the Schmidt decomposition. Carroll and co-workers studied the Schmidt decomposition of a unitary operator. And it follows from this fact that actually this is implied by the fact that the unitary operator U has maximum operator entanglement. So, so this is a dual unitary. So a dual unitary is just a unitary operator whose rearrangement or realignment is also unitary. And if you make a circuit out of this, it will be a dual unitary circuit. We'll come back to this point a little bit later, but what is nice about having these dual unitary circuits is that you can calculate, as I said, these kind of correlations exactly. So especially what has been calculated is really only single particle correlators. So to find single particle correlators between two sites, localized observables at, let's say, X and Y, any general operator can be expanded in terms of an operator basis, and therefore it's sufficient for us to look at what happens to an operator basis. So we can look at what happens to an orthogonal operator basis, and the identity can be treated separately. It's not very important, but and therefore we will only look at the non-identity parts of this operator basis. And so because it's an orthogonal operator, therefore the trace will be equal to 0. But these are not really very essential points. It just makes our life more easier. We don't have to write the other term in the correlation. So so finding such correlation between sites X and Y, and these are the bases AI and AJ. Okay, so so we are evolving one of it with time. And the other is not evolved with time, and then we are finding out what is this. So the trace of this, and this is given by this diagram. Again, we just follow through this. So u to the power of t. So you put the layers of u here, t of them. And then comes this operator at some point. And then you have the adjoint. And then you have this. So the adjoint is u power minus t. And then you have this other observable here. And the trace is being taken care of by the contraction. So the whole thing is on a torus. So, so that's the trace operation.
There was a question from the audience. Is this diagram oriented? Whether the bottom and the top legs are different?
They are connected by, as I said, they're on a torus. So this would be connected to this.
Okay.
And this would be connected to this and so on. Because
and left side is connected to right side. So this is kind of a torus.
It is a torus. Yeah.
Okay. Good. So I hope it answers the question of.
Otherwise I don't know what orientation, what exactly is meant.
Thanks.
Okay, so this is going back to the paper of Bertini. So they showed that such correlations vanish everywhere except on the light cone, and the light cone means that x minus y minus x is equal to t. Okay, so in order to see that, actually you can just use unitarity. Like for example, let's look at this picture. Look at this. These two at the interface. Since it's an u and u adjoint, you can just apply this identity operation here. So these things will get contracted away and they will just disappear. And so all of these will disappear. They will all get contracted just from unitarity, and you will get such a picture. You will get such a picture in which you have one of the operators inside here and here. So this is the light cone. And I mean, these are the edges are the light cones. And further, now one can make use of the fact that the realigned operator is also is also unitary to actually make some further contractions. And so there are these further contractions which happen because it's a dual unitary. And then what you will see is that this can be propagated and till you are contracting this whole thing. So but the trace of this operator is 0, and therefore this correlation vanishes. So if you have an operator inside here, inside the light cone with respect to this operator, then the correlation vanishes anywhere inside the light cone. And on the light cone also, there are two possibilities. It's on the left or on the right of this, like here, and this also vanishes. So the only thing that remains and that does not vanish is the correlations along the light cone. And this is happening because of duality. Okay, there is no correlation inside the light cone. On the light cone, this is just this is true actually, even if you have just unitarity, that this picture holds. On the light cone, if you want to find the correlations, you just have to find this. Okay, so now it's an interesting diagram, because what one notices from this is that there is an nested structure here. If you take the central part of it and replace it by one operator, it looks exactly like the one on one above. And so this nested structure is what is very important and actually gives rise to a drastic simplification, that we can find the correlation by looking at the central part of it, which I have characterized here. I have made it bigger. We just have to iterate that as a map. We have to iterate that 2t times and then act on it with this operator here. Okay, so this is the key point, and therefore we can find the correlation as an action of a. Do you hear fireworks?
Yes. Please.
Sorry, it is out of my control. I don't know what is there to celebrate at this point. But,
yes, but
yes.
Is it on your side?
Yes, it's on my side.
Okay,
so
okay. So we are not okay. Good. So we have to start like this. Okay.
uh, so um, so here we have a map M plus, represented here as M plus. It's a map which is going to take these operators into other operators, but we just have to iterate this map 2t times to find this. So there are these CPTP maps. So this is actually a completely positive trace preserving map, which takes single particle observables to other single particle observables. And there are two of them. So the M plus, which is actually directly relevant to this diagram, is given by this. So this U is the basic two particle unitary brick that's making this circuit. And this sigma is just this representing this inner operator, A beta, okay? And the identity here is representing the fact that there's no such operator on the other side. And here the trace is over the first system, where the identity is not there, okay? So this is slightly different from the usual case where one thinks about this as the environment, and then you're tracing out the environment. Here you're tracing out the system, and so this is the map, and that map is represented by this diagram, which is just this one. So the partial trace is given by this. By this.
So a short remark: such channels are also called complementary channels,
Yes.
where you trace out the system and leave environment.
Yes, exactly. Yes. Thanks for pointing out, Carol. I didn't know about this, but yes. So these are complementary, but it's interesting what it is complementary to. I'll come to that in a moment. M minus, on the other hand, is another map which is also still, tracing out the system. But now this is a map relevant. This is the relevant map if this operator is sitting on the right leg of this unitary. So because there is not necessarily a symmetry between, or parity symmetry between these two legs, this is in general a different map. Okay, but these two are not complementary to each other. So these are just two different maps.
Mm-hmm.
Okay. So these are, so they since they are unital maps, they preserve the identity, they are contractive, so it has all the properties of a usual CPTP map. Just to recall a few of these things, so the spectrum, the eigenvalues of these maps play a very important role, because they actually determine how the correlations are going to behave with time. And we are going to generically call them just lambda j, and plus minus for the two channels. And there are q square minus 1 such numbers each. But for both m plus and m minus, there is an eigenvalue which is equal to 1, which just corresponds to the identity operator, the initial one, which does not change. So that's a trivial eigenvalue. So we will just call that a trivial eigenvalue and ignore it for most part. And the other eigenvalues are all less than 1. And we will order them such that lambda 1 is the largest, and so on. So the smallest eigenvalue in modulus, they are in general complex, in modulus is lambda q square minus 1. And they completely determine the correlation functions, because the correlation functions in general, and this is along the light cone, so that means that x is plus or minus t. Here, one of the operators is at the origin, is equal to the superpositions of these eigenvalues raised to the power of time, to t. Okay, so the properties of the circuit depend crucially on the eigenvalues of the CPTP maps. And they are coming from this two-particle unitary itself. So there's an ergodic classification as suggested in this paper by Bertini, Koch, and Prosen, which I recall here, that the non-trivial eigenvalues determine the ergodic properties. A non-interacting one is when all the non-trivial eigenvalues are equal to 1. the correlations remain constant in all modes and the system is non-interacting. So the least interesting case, it's non-ergodic, interacting and non-integrable, but interacting and non-integrable if you have a certain number of non-trivial eigenvalues exactly equal to 1. Then the correlations in those modes, k of them, let's say, remain constant. So it's not ergodic. If you take an average correlation, it won't decay to 0. An ergodic but non-mixing one is when all the eigenvalues none of the eigenvalues is equal to 1 exactly, so that none of the modes are just fixed. And I'm talking about the non-trivial modes, of course. But there exists at least one eigenvalue whose unit modulus is 1. So this one is ergodic. So at least one of them lies on the unit circle. Okay, so that will be still ergodic because you will find that the average is equal to 0. The average correlation is equal to 0, but it's non-mixing because modes with that are not decaying. Ergodic and mixing is the case when all of the eigenvalues are strictly within the unit circle. Okay, then the correlations decay exponentially. So I think there is no need for us to look at a Kolmogorov intermediate step. All of them are mixing in this particular dual circuits.
So one more remark. This ergodic and mixing, this condition means that there exists a spectral gap. So the second largest eigenvalue is smaller than 1. And the size of the spectral gap, 1 minus absolute value of lambda 2, determines the speed of correlations decay, yes?
Yes, yes. So there is some subtlety also about whether, the cases when you have non-diagonalizable M, which I mean, these maps, which also happens, but you're right. I mean, you expect there to be a gap, and the spectral gap actually determines the. I'll come to that in a minute.
Mm-hmm.
So we have added this particular bit, which is the apex of it, is when all the eigenvalues are strictly equal to 0. All the non-trivial eigenvalues.
Of course, all non-trivial.
All non-trivial eigenvalues vanish in both the maps M plus and M minus.
Mm-hmm, mm-hmm.
Okay. So then the correlations vanish instantly. So that's the Bernoulli circuit. So just as a kind of an overview of what's going to come, I think maybe I have half an hour, Carol?
Yes, wow. Mm-hmm.
Okay, good. I say 16 out of 30. That's about half of my talk.
Yes.
Maybe less. Okay, so here is a rudimentary phase diagram, sort of picture where I will talk about entangling power in a short while, but actually entangling power of this brick or this two-particle unitary plays a rather crucial role. And that's our main point, which we will come to again and again. And here is this picture which shows this clearly. If the entangling power is 0 of this two-particle unitary U, then it is either a swap or it is locally equivalent to a swap, in which case it is non-mixing. As long as the entangling power is not 0, it can be mixing. It can be ergodic also. It can be ergodic and non-mixing, but it can. I'm sorry. Yes, but it can be mixing as well. Okay, so all you need is a little bit of entangling power in the sense that it's just non-zero. It's possible to make it mixing, as we will. But there is a threshold, interestingly. There's a threshold, which is very simple threshold to write in terms of these local dimensions Q, that if the entangling power is larger than this threshold, it's guaranteed to be mixing. All the eigenvalues will be strictly less than 1 in modulus. And interestingly, it's a tight bound in the sense that there are systems in which the entangling power is equal to this EP star, in which it is not mixing. Okay, but if it is just above that, it's guaranteed to be mixing. And if the entangling power is equal to 1, it's a case of Bernoulli, when all the eigenvalues are strictly equal to 0, and in which case actually the two-particle unitary is a two-unitary which I will define in a minute. So we may think about this entangling power as some kind of an interaction. And what's happening is that beyond this value of EP star, the interaction is so large that come what may in terms of single particle dynamics, the system is always mixing. Okay, so we'll take a more closer look at these maps. What exactly are they? This is the map as I wrote it, and we notice that the product of a partial transpose times as a joint has a very similar structure. In terms of contractions, what you're contracting is two legs of the diagonals, if you wish. Okay, so here is this diagonal of the green going into this diagonal, and this diagonal being contracted with that. And this looks exactly the same, and in fact, it's very closely related. This CPTP map can be represented in terms of its action on vectors. So it's kind of just a vectorization of this map. In terms of this matrix, the Q square dimensional matrix, M plus, where this M plus is given in terms of a partial transpose in this manner. So it's just a product of partial transpose times it's a joint and then a realignment of this. So the fact that, so this is, I think, called the dynamical matrix, correct? I think that's the positive matrix, and this is the map itself. So the fact that it's a
dynamical matrix, sorry, or Choi matrix is the same.
Choi matrix, yeah.
By the way, dynamical matrix, this name goes back to the paper by
Sudarshan, I guess.
Sudarshan, yes, one of the first papers, many years earlier before Choi. So there is an Indian trace.
Well, he was born Indian, yes. So indeed. So, but the interesting thing, I mean, Carol, if you now ask what is the complementary map to this, that would have an R here. That would have a realignment operation on this. But since it's a dual operation, dual operators, that would be simply identity. Identity realigned. So which would be actually a maximally, that would be a rank 1 projector.
Yes.
That would be a rank 1 projector. So actually I mean, the complementary map is, I think, the channel for correlations at x equal to 0. That is an autocorrelation function. So the complementary maps are actually, one is along the light cone, while the other is along the x equal to 0 line. So this is what I think is happening. And the M minus is just a swap of these two. So you can see that that's connected by the swap of this channel M plus. Okay. So these maps therefore can be written, have a natural form in terms of partial transpose and partial and realignment, two of the key operations for a bipartite unitary. And therefore we can define a T duality as an operator U, which is unitary and whose partial transpose is also unitary. Okay, in which case this contraction will hold. And similarly this. Okay, so there is further diagrams which will simplify, and this implies a totally depolarizing channel, because if you have a unitary which is both dual and T-dual, then as we just saw here, this would now become identity, and the identity's realignment is just the maximally entangled state. So it's so that's just a rank 1 projector, and indeed all the eigenvalues are equal to 0 except 1, which is the trivial eigenvalue corresponding to this eigenstate phi plus. And therefore, in this case, you will have Bernoulli circuits. And it doesn't matter whether it is plus or minus, because the other channel is also the same. So that is the reverse of this. So if it is T dual, both of them are identity. So you don't have to worry about the other channel. Automatically, it would also be, all the eigenvalues would vanish. And therefore, if it is both dual and T dual, this has been called, I think, two unitary for the first time in this paper. Am I correct, Carol? Okay, so that's a two unitary operator, and therefore this is also equivalently related to absolutely maximally entangled states. You can define a four-party state using this operator U like this, and then it would be an absolutely maximally entangled state in the sense that any bipartite cut is maximally mixed. The state is maximally mixed. So it's an absolutely maximally entangled state of four parties. So two unitary circuits constructed out of these are Bernoulli, in the sense that you have single particle correlation between single particles vanishing at any space-time separated points, okay, from this. But actually, quite interestingly, it also follows that two particle observables also decorrelate instantaneously. So that is seen from, again, pictures such as these, where you have these two operators sitting here. And now if you make use of the T duality, it breaks this link as well, and then they will decorrelate. But actually, no other, like three particle observables do not decorrelate instantaneously. So it's interesting that maybe it's something like a Bernoulli partition. What are the observables which decorrelate instantaneously? A single particle and two particle observables decorrelates instantaneously. And this must be related to the fact that it's a two particle unitary which is building up this entire circuit.
So basically any two unitary circuits are Bernoulli.
Yes.
Yes, okay. Anyway, so I will just mention that our colleague Dardo Goshenece, whom you quote, is also here among us. He came from Chile, yes.
Hi, Dardo. Well,
it's very early for him.
Hello, Arul.
No, early for him, I see. Okay, all right. I think I have to take a time test. Carol, how much time do I have?
Well, at least 15 minutes.
15 minutes. Okay. So let's see. So maybe I will, so I need to introduce the entangling power just for sake of completeness, because that plays actually an important role in this thing here. So, so it's just a bipartite operator U, and we take unentangled states, and we calculate an entanglement measure on this, and then average over all the product states. This is called an entangling power, or I should have given the reference of Zanardi to 2000, 2001, who defined it first, I think, and who studied this. So we take Haar measure for phi1 and phi2. So if the state itself is given by this, then the partial trace is this reduced density matrix. And if we take the linear entropy as the measure of entanglement in this pure state, then the average of this over this entire, the Haar average, has a nice expression. In terms of the dimensionalities, it's just this constant C, which is sitting there. But in terms of these operator entanglements of U itself and U times the swap, okay, where this S is a swap which has a maximum operator entanglement. Now this CQ here is put in there so that the range of this entangling power is from 0 to 1. So 1 is the case when it is maximally entangling, and 0 is when it's a product. So the operator entanglements here are defined in terms of, can be defined, are actually defined in terms of the Schmidt decomposition of this unitary U, but it's completely equivalent in terms of the realignment operations and partial transpose operations, which we have already defined to be just a purity of density matrices defined by these defined by the realignment. So that is actually the operator entanglement E of U. And you notice that if it is a dual operator, this is identity, and this is in fact then maximum is equal to E of S. And this is what I said, U is dual if and only if it is maximally entangled, in the sense that E of U is the maximum possible. Now this EUS is complementary to it, and that is given in terms of the partial transpose, and that is maximum if and only if U is T dual, or is maximally, or if US is maximally entangled. And therefore, this EP of U is a maximum and is equal to 1 if and only if U is a 2-unitary, which is also sometimes referred to as perfect tensor in this case. So the entangling power is maximum in these cases. So now now we're going to ask what is the action of local unitary operators on this two-particle unitary U. Okay. Now, if you have any local operation on these two-particle unitaries U, let's say that we define an U prime with these being local unitaries, single particle unitaries, then U prime is also dual because it still remains maximally entangled. And therefore, you can construct a dual unitary circuit just based on these U primes. Okay. So in particular, therefore, E of U prime is equal to E of U, as well as the entangling power is this. So these are local unitary invariants. However, the circuits, although they remain dual, they are not invariant. The maps are changing themselves. Okay, so these CPTP maps are changing, and the way they change is given by this. So the map corresponding to U prime is given by the map corresponding to U by the action on the left and right of this. So you notice that actually there are 4 local operators here. 2 of them enter this M plus, U1 and V2. The other 2 will enter a similar equation for M minus. Okay, but importantly, this is not a similarity or unitary transformation, and therefore the eigenvalues are not the same. The eigenvalues of M plus U prime is not the same as the eigenvalues of this. So now we want to look at what happens to these eigenvalues of these channels under these local operations. So let me show you this picture here of taking 4 dual unitary operators, and we construct these dual unitary operators in a simple way. We take a diagonal unitary filled with faces multiplied by a swap. This gives you a dual unitary. Okay, so we take 4 such operators, fix them. They will have these entangling powers, which are written out here on top. And then we multiply them by random locals, hard measure of random locals. I forget how many, maybe 1,000 or something. And then we find the eigenvalues of these channels and we plot them here.
So what is blue, what is red?
Yes, good question. So blue is the largest eigenvalue. So that's lambda 1. And the other is the smallest eigenvalue. Okay, the in-between eigenvalues we have not plotted for clarity. Okay, so they're all lying somewhere in between these rings. So you can see that for small entangling power, all of them are clustering almost on top of each other, which is to be expected. And then as the entangling power is increasing, there is a divergence. And as you can see here, there is a clear distinction between these eigenvalues. And this is the largest entangling power in this 4 categories here. But what is interesting is also that we have plotted a circle here. I don't know whether that's very clear. It's clear in this picture, a black circle. The black circle corresponds to a circle of radius square root 1 minus the entangling power, EP. So you see that that fits this eigenvalue lambda 1 quite nicely. And in fact, we will see why that is so. So now we define these mixing rates and some maximum and minimum mixing rates. So we look at the spectral gap, which is 1 minus the largest eigenvalue. I mean, the largest eigenvalue is the weakest link. If that is smaller than 1, the circuit is mixing, and the farther away it is from 1, the more mixing it is. And the smallest it can be is 0, as in the Bernoulli circuit. And the mixing rates, because these are all exponential, we can define them as a logarithm of these. And we can define a maximum mixing rate, which is a maximum of mu1, where we are maximizing over all the local unitaries, u, so that we are removing the information about the local unitary, and it's only a function of the non-local content of the two-particle unitaries. Okay, so this is the maximum mixing rate possible, assuming that you have control over single particle unitaries, okay, or single particle fields. And similarly, we can define an average mixing rate where we average over all the single particle unitaries, again, in a Haar random manner. So by construction, the maximum mixing rate and the average mixing rates are local unitary invariant, unlike the mixing rates themselves. And for qubits here, I'm showing results for qubits for both of these things, nu plus. So it's a bit of a busy graph. I would say ignore the blue curve. The red curve is for the case when these are Haar measure unitaries. And the one outside, the main one is the nu, the maximum mixing rate. What is plotted is a maximum mixing rate for qubits versus entangling power. And there is an analytical curve also, which is plotted in here. So it's actually possible to analytically find this for qubits. And by the way, I should mention that for qubits, the dual unitaries have a very simple representation. In terms of the Cartan decomposition, it's pi by 4, and there's a single parameter j, which is parameterizing the dual circuits. Mm-hmm. I mean the two qubit dual operators.
Yeah. So I will only add that the famous Fourier matrix belongs to this class. Yes.
Yes. Yes. So in fact, the Fourier belongs to this in any dimension, any local dimension. Mm-hmm. Mm-hmm. Now the maximum mixing rate is interestingly given by this. So there's a -1/3 log of this, where this EP max is 2/3. As we know, there is a qubits are special cases where the maximum entangling power is not 1, but is only 2/3. That's because there are no two unitaries for qubits. Mm-hmm. And that is reflected in this fact that this is not 1, but is 2/3. And this is what is plotted here. So it fits very well the numerics. We don't have an analytical form for the average mixing rate, strangely. For the case of qubits, we have, but we can say one thing, that the maximum of this average mixing rate is equal to 1. So in fact, you can see the inset is the average, and you can see that it just reaches 1. So when U is the maximum possible entangling power for qubits, the average mixing rate is just 1. Mm-hmm. So we will actually contrast this with Q greater than 2 shortly. So what we see is there is a universality for any local dimension Q which is greater than 2. So Q trits and above. So here we are plotting the expectation value or the average of the largest eigenvalues modulus. So lambda 1 modulus, the average is over single particle unitaries. Okay, so we're just looking at the largest average of the largest non-trivial eigenvalue. This is versus the entangling power of this gate here. And
some 5 minutes more?
Yeah, okay, thanks. So you can see that there is this, it falls on this single curve for Q is 3, 4, 5, and 6. Okay, and this is qubits. Qubits are special. They don't fall on this universal curve. But what is interesting is that whatever may be the source of your dual unitary, and there are several sources of these dual unitaries, the average mixing rate is a one-to-one function of the entangling power. And this function is very close to square root of 1 minus EP, which recall was the circle radius in that figure where we showed the eigenvalues themselves. And we can understand the square root 1 minus EP from trying to estimate the largest eigenvalue. So what we did was to find an M tilde, was to just to subtract away the trivial eigenvalue, remove that, and then try to find the largest eigenvalue by finding the norm of this matrix raised to the power of k, and then in the limit k tending towards infinity, trying to estimate this. And so you can see the paper for our estimate of this, and that turned out to be, in fact, approximately the square root 1 minus EP. So I think we can understand why this is so in this case. So just some more observations regarding larger dimensions. So this is Q is 3. We are now plotting here the mixing rates. So this is nu and this is mu, the average and maximum versus entangling power. Again, you can see that the average does in fact have a one-to-one function with the entangling power. And the inset is for another set of dual unitaries. Okay, so they are ensembles of dual unitaries. But what is interesting is that nu is not a one-to-one function as a function of EP. So although it's a local unitary invariant, it has some more information than just the entangling power. Okay, so I think I will, yeah. So again, this entangling power, the simplest way in which it arises is through the norm of these channels. And what is interesting is that the channel norm, just the norm of the channel, is a local unitary invariant, and that is just directly related to the entangling power. It's a simple exercise to show this. However, and in fact, that implies a bunch of inequalities for the eigenvalues, which I will mention in the next slide. But I just want to say that the powers of them are not local unitary invariant, and in fact, that's what gives rise to these to the square root of 1 minus EP. And these increasing powers, which are used in this formula to find the largest eigenvalue, has this particular form. So if you raise it to the power of k, it's 1 minus EP raised to the power of k, but the factor q square minus 1 remains exactly what it is, and therefore it disappears when you're taking the whole thing raised to the power of 1 over k, and k goes to infinity. So the only thing that remains is this factor here. Okay, so the norm conditions actually give a more powerful conditions for, or sufficiency conditions for mixing. It says that there are a series of entangling powers such that if your entangling power of a two-particle unitary is crossing the threshold, you are ensured that certain number of eigenvalues is less than 1. So for example, if the entangling power is just greater than 0, you are ensured that the smallest eigenvalue is smaller than 1, and there will be at least one mixing mode. If the entangling power is more than 1 by q square minus 1, then there will be 2 modes which are guaranteed to be mixing, and so on, till EP star, when all the modes are guaranteed to be mixing. So we see this actually in permutations. Here we have taken all dual unitary permutations for Q is 3, and the blue is the largest eigenvalue modulus as a function of entangling power. And this dotted line here is this entangling power of these is actually this EP star, this, threshold. So the largest eigenvalue can be equal to 1 before the threshold, but once it is crossed, it has come down. And this is an example of a Bernoulli. So it's a two unitary. And similarly, this is the second eigenvalue, and this is the other threshold. Okay, so summary of these consequences. So there's a sufficient condition for mixing. If this entangling power is larger than this, then all the eigenvalues are less than 1. Circuit is mixing. The interactions are so strong that basically no local fields can localize the correlations. And if and only if the entangling power is 1, the circuit is Bernoulli. Therefore, there are no Bernoulli circuits for qubits. And yes, as I said, as long as entangling power is non-zero, you have at least one mixing mode. And the only non-interacting circuits are when unitary is S, and those with all modes non-decaying are local unitary equivalent to the swap. And local unitary Haar averaged largest eigenvalue is very simply given by this. So, so there is in the paper which we have put out on the archive, several ways of constructing dual unitaries, because it's interesting to also construct dual unitaries with very large entangling power. So I just advertised this recent work where we have a method of constructing these things, dual unitary operators with large entangling powers. But in this recent paper, we've also given several analytical ways of constructing dual unitary operators. Okay, so summary. So we've defined Bernoulli circuits as those constructed from two unitaries, and they are in some sense at an apex of a quantum ergodic hierarchy. And yeah, so I've already, I think, said some of these things quite now. So the way forward, there are several interesting questions, especially non-dual circuits. There's already some work out there. But I think from the point of view of entangling power, I think it holds a lot of interest, because this is a picture which is there in a work with Carroll and others, which is entangling power on this side. And this one here is a difference between operator entanglement and E of U and E of US. So there are two local unitary invariants. So this is what we call gate typicality. I just turned the picture around 90 degrees so that it looks like an apex. So here is a two unitary, and this entire line is dual. So that's the dual road to this. Incidentally, this is for qubits. There seems to be a gap, and that gap seems to be real. So it's not connected. This road seems to, you need to take a detour to go in if you want to be connected to that. But it's still a conjecture. But there can be several other interesting roads. One is along this, which is along the T-dual road. But we don't know how to calculate correlations in this. But there could be other roads also which are interesting. And what happens to finite circuits for times which are larger than L by 2, connections with standard quantum chaos measures, and physical models of Bernoulli circuits. We have some examples from a cat map, which is also related to the Fourier, but it'll be interesting to actually construct physical models. So thank you.
Thank you very much. So we start the discussion. Who would like to ask a first question? Konrad, are you prepared to ask something? Not yet.
I had a question, but from the, very beginning, I think it was the first two slides about the Baker's map, because yeah. Oh yes, exactly this. This slide. So is it really true that Baker's map, immediately kills all correlations between any perhaps variables? Because it doesn't look like it.
So
this.
No, as I said, it has to be non-zero on Bernoulli partition. So like, for example, if you take a characteristic function which is localized on the left vertical half here, then it would have indeed that property. Or you could look at any of the generating partitions. So then the correlations would be 0, but otherwise not. They would exponentially decay. So you just take 2x modulo 1 or 2q modulo 1. the doubling map, the correlations will be decaying in general exponentially. They will only vanish instantaneously for those which are partitioned, where you have a good symbolic sequence for each of these partitions.
So Bernoulli dynamics is when there is some kind of a partition of the system into several parts that this holds.
So yeah, so a Bernoulli system is something which has a exact symbolic dynamics on which the dynamics is a left shift. So not just not just a, what is it called, subshift. It has to be a
I
full,
see, because it is a bit shift of sorts. Yes.
Like for example, a cat map is not Bernoulli. It is a C system supposedly.
So, Arul, the simplest example of your quantum Bernoulli system is represented by a matrix, unitary matrix of size 9. Is it so?
Yes.
So there are some people in the audience who worked on AME states, absolutely maximally entangled. I'm not so sure whether it was clear that your construction shows that there's a special applications for those AME states, yes? Because each AME state, from your perspective, defines such a Bernoulli system,
Absolutely.
Yes?
Absolutely. Yes.
Yes, yes. So for those who like AME, you found for them a new application.
Yes, you could say that.
Are there any other questions?
I've got one question, but don't know, does it make any sense?
Go ahead.
When we were constructing time evolutions, let's say using unitary operators, the information could propagate with constant speed, let's say, because of structure of this net. And are there any more extended model when the net is more complicated or something like that?
You mean like where it includes more than two particles?
I mean like connections between subsystems are not only between nearest neighbors, but some longer connections.
Right, right. No, it's an interesting question. I'm not aware of any work myself at this point, but it's definitely interesting for the following reason. We don't have Bernoulli circuits for qubits, but if you have interactions between three particles, I think you can have Bernoulli circuits in that case. So for qubits, you would have Bernoulli circuits in that case. You could and also the probably the support of your systems for which support of the observables for which it remains. I mean, the correlations vanish may also increase from just 2-party to 3-party. But as far as I know, there is no work with more than 2-particle interaction. But it's absolutely conceivable that that's the case. That's possible.
Are there some more questions? So, Arul, I'm pretty sure we'll have a lot of questions to discuss later on. Let me now thank you on behalf of all of us.